There is a continent at the bottom of the Indian Ocean. Not a ridge, not a seamount, not an ordinary underwater plateau built from volcanic rock piling up on the seafloor. A continent with continental crust, with a geological history that includes forests and rivers and wildfires and rain. A landmass that was once above the surface of the sea, that may have been home to dense conifer forests in the age of the dinosaurs, and that has been lying under 1 to 2 kilometers of cold southern ocean water for the last 20 million years, waiting to be understood. It is called the Kerguelen Plateau, and it is one of the strangest and least discussed geological features on Earth. It stretches more than 2,200 kilometers from northwest to southeast beneath the southern Indian Ocean, covering an area larger than India, nearly 3 times the size of Japan, and the only part of it that breaks the surface today is a cluster of remote, windswept islands that very few people have ever visited and that sit at the end of the world, battered by the furious winds of the Southern Ocean, with no other land for thousands of kilometers in any direction. Welcome to Sleepy Science Stories. Tonight we go deep, not into space but into the Earth itself, into the geological past of a planet that has been rearranging itself for 4.5 billion years, tearing continents apart and assembling new ones, lifting land above the sea, and then dragging it back under, creating and destroying entire worlds over timescales that dwarf anything in human experience. The Kerguelen Plateau is one chapter in that story, and it is a chapter that contains forests and volcanoes and floods of lava larger than anything humans have ever witnessed, and the slow, inexorable sinking of an entire continent into the deep. It is sometimes called the real Atlantis by scientists who mean something very different from the mythological sense. Not a lost civilization, but a lost landmass, a place that genuinely existed above the waves, that genuinely sank, and that left behind enough geological evidence that we can reconstruct, with some confidence, what it looked like, and what lived there. Let your breathing slow. Let the room settle around you. Tonight we go back 130 million years, to the beginning of a story that ends at the bottom of the sea, and that is still, right now, being told. The Kerguelen Plateau is not famous in the way that Chernobyl, or the Mariana Trench, or the Great Barrier Reef are famous. It appears on no map that most people have ever looked at. It is not visible from space in any recognizable way. It was not discovered until the 18th century, and its true geological character was not understood until the 20th. But it is one of the most scientifically significant geological features on the planet, and the story it tells about how continents form, flourish, and disappear is one of the most complete and most astonishing in the geological record. Tonight we tell that story from the beginning, in the warm Cretaceous world where it started, through the forests and the fires and the rivers and the charcoal that is still preserved in the rock today, to the cold, dark, deep ocean where the lost continent now lies, patient and preserved and still yielding its secrets to the scientists who go looking for it. This is the story of a real Atlantis, one that science has actually found. To understand how the Kerguelen Plateau came to exist and why it ended up where it did, it is necessary to go back to a time when the geography of Earth was completely unrecognizable, when the continents were arranged in patterns that have no analog in any map we use today. 130 million years ago, the southern hemisphere was dominated by a supercontinent called Gondwana, a vast landmass that had been assembled hundreds of millions of years earlier from the pieces that would eventually become Africa, South America, Antarctica, Australia, and India. Gondwana had been holding together since well before the age of the dinosaurs, and its interior was a world unto itself, with its own climate, its own ecosystems, its own rivers and mountains and forests, all connected across what is now thousands of kilometers of open ocean. But Gondwana was already beginning to break apart. The forces that drive continental drift, the convection currents in the Earth's mantle that slowly move the tectonic plates, were working at the boundaries of the supercontinent, pulling its pieces apart, opening rifts that would eventually become ocean basins. had already begun separating from South America. India was beginning its long journey northward, on the way to the collision with Asia that would eventually raise the Himalayas. Antarctica was drifting toward the South Pole. Australia was moving in its own direction. The breakup of Gondwana was not clean or simple. It did not happen like a plate of glass shattering into a few large pieces. It happened gradually, over tens of millions of years, with some pieces separating early and others remaining connected long after the initial rifting began. Smaller fragments of continental crust were left behind as the major pieces moved, stranded in the widening ocean basins like islands of ancient rock adrift in a sea of younger material. And as the rifts opened, something else was happening deep beneath the surface of the Earth. A column of abnormally hot mantle rock, called a mantle plume or hotspot, was rising toward the crust in the region between India and Antarctica, generating enormous volumes of molten rock that poured out at the surface in what geologists call a flood basalt event, one of the most violent kinds of volcanic activity the planet experiences. That hotspot would become the engine that built the Kerguelen Plateau, and its effects on the geography of the southern Indian Ocean would persist for over 100 million years, from the time of the dinosaurs to the present day. The story of the Kerguelen Plateau is inseparable from the story of this hotspot, which is still active today, still erupting at the remote Heard and McDonald Islands that mark the only portion of the plateau that remains above the waves. The world of Gondwana is also the world that produced so many of the geological features we now think of as fixed and permanent. The Indian Ocean did not exist. The Atlantic was a narrow seaway barely wider than the present-day Red Sea. The continents were assembled in configurations that would be unrecognizable on any modern map, and the forces that were tearing them apart were also building new landmasses in the gaps they left behind. The Kerguelen Plateau is one of those new landmasses, born from the violence of Gondwana's dissolution and shaped by the particular combination of tectonic and volcanic forces that operated in this corner of the fragmenting supercontinent. Its story begins not with a single dramatic event, but with the slow accumulation of geological processes operating over tens of millions of years, a reminder that the most extraordinary features of Earth's surface are usually the product of patience rather than catastrophe, of steady forces applied over durations that dwarf anything in human history. The Kerguelen hotspot began making its presence known approximately 130 million years ago, at the same time as the eastern Indian Ocean was beginning to open. What it produced was not an ordinary volcanic eruption, but something on a scale that makes the largest historic volcanic events seem trivial by comparison. A flood basalt event is what happens when a mantle plume delivers an extraordinary volume of molten rock to the base of the lithosphere, and it erupts at the surface in pulses that last for hundreds of thousands to millions of years. The lava does not emerge from a single volcano in the familiar fashion, but pours out from long fissures in the ground, spreading across the landscape in sheets that can be hundreds of meters thick and cover areas of thousands of square kilometers in a single eruptive episode. Over the duration of the event, these sheets stack on top of one another, building a plateau of solidified lava whose volume is staggering. The Kerguelen flood basalt was one of the largest such events in the last 200 million years of Earth history. The total volume of igneous rock produced by the Kerguelen hotspot, including the plateau itself, the broken ridge that was once part of it, the 90 East ridge that marks its track across the ocean floor, and the various fragments of continental and oceanic crust associated with it, is estimated at tens of millions of cubic kilometers. The eruptions peaked between approximately 120 and 95 million years ago, during which the hotspot was at its most productive, generating the central and southern portions of the plateau that are now the largest part of the feature. The early eruptions occurred in an environment that was transitional between continental and oceanic, as the Indian and Antarctic plates were just beginning to separate, and the crust beneath the emerging plateau was a mixture of older continental fragments from Gondwana and newly generated igneous rock from the hotspot itself. This mixed origin is one of the distinctive features of the Kerguelen Plateau compared to purely oceanic plateaus like the Ontong Java Plateau in the Pacific, and it is the source of the continental material that makes the plateau scientifically distinctive and geologically interesting. The scale of the volcanism that built the Kerguelen Plateau had consequences beyond the local geology. Flood basalt events of this magnitude release enormous quantities of gases into the atmosphere, particularly carbon dioxide, sulfur dioxide, and water vapor, and can drive significant climate change over the periods of peak eruption. The Cretaceous was already a warm period by geological standards, with no permanent polar ice and sea levels significantly higher than today, and the Kerguelen eruptions may have contributed to the warmth of the mid-Cretaceous climatic optimum, the warmest sustained period in the last 200 million years. The period of peak Kerguelen volcanism, between approximately 120 and 95 million years ago, coincides with one of the most extreme warm periods in Cretaceous history, when tropical marine temperatures may have reached levels that are difficult to reconcile with any modern analog. Whether the Kerguelen eruptions drove this warming or simply coincided with it is debated, but the connection between large igneous provinces and global climate events is a recognized pattern in Earth history, seen repeatedly in the geological record from the Permian-Triassic boundary to the end Cretaceous. The Kerguelen Plateau is one of the data points in that pattern, a reminder that volcanism on the scale of a large igneous province is not just a local geological event, but a planetary one. Here is the fact about the Kerguelen Plateau that most people find hardest to absorb. For much of its history, it was not underwater at all. The evidence that the plateau was once above sea level is concrete, physical, and was recovered from the seafloor by scientific drilling ships that brought up cores of sediment and rock from beneath the ocean. In those cores, researchers found dark brown soil layers sitting directly on top of basalt lava flows. They found charcoal, the product of ancient wildfires. They found conglomerates, rounded river stones that could only have been produced by water flowing over land. They found fragments of fossilized wood. All of these things require land, not ocean. They are the calling cards of a surface environment where plants grew, lightning started fires, and rivers carried sediment. The plateau was above sea level not once but at least 3 times during an 80 million year period, from approximately 100 million years ago to about 20 million years ago, when it finally sank below the surface for the last time. The 3 periods of emergence correspond to peaks in volcanic activity that periodically raised the plateau back above the waterline as fresh lava added volume and buoyancy, between periods when subsidence pulled it back below. During the periods when it stood above the waves, the Kerguelen microcontinent was not a barren volcanic rock. At its maximum extent, the southern portion alone may have covered an area of approximately 500,000 square kilometers, comparable in size to Spain, and it rose to elevations of 1 to 2 kilometers above sea level. This was a substantial landmass, with enough elevation to generate its own weather patterns, with rivers draining its slopes, and with enough stability to support forests. The fossil evidence tells us what kind of forests. Wood fragments recovered from drill cores at the Kerguelen Islands were identified as belonging to Araucarian conifers and cypresses, trees related to the modern Norfolk Island pine and the Patagonian cypress, whose living relatives grow today in South America, Australia, and the Pacific Islands. Similar fossil wood has been found across the southern hemisphere, evidence of a once continuous southern forest that thrived when Gondwana was still partially assembled, and the southern landmasses shared a climate and a flora. The Kerguelen microcontinent, in its periods of emergence, was part of this southern world, a forested island in the developing Indian Ocean, inhabited by the plants and presumably the animals that characterized the southern continents in the Cretaceous, during the age of the dinosaurs. It was not a stepping stone between continents, because the plateau never bridged the gap between India and Antarctica, as some early researchers speculated, but it was a real landmass with a real ecology, one that left its record in the charcoal and the wood fragments and the river stones that now lie under more than a kilometer of cold ocean. The physical evidence for subaerial existence is also evidence for a particular kind of geological process: the ability of large igneous provinces to maintain significant portions of their area above sea level for extended periods despite the general tendency of oceanic crust to subside as it cools. The Kerguelen Plateau managed this through the combination of its extraordinary thickness, in places more than 30 kilometers compared to typical oceanic crust of 5 to 8 kilometers, the buoyancy provided by the partly continental material in its foundation, and the periodic renewal of volcanic activity that added new material and raised the plateau back above the waterline. Understanding how these factors interacted and what proportion of each was responsible for maintaining the plateau at or above sea level during each of its subaerial periods is one of the scientific questions that continues to be investigated using the drill core archive. The answer matters not only for the Kerguelen story but for understanding how other large igneous provinces around the world behaved during their formation, and what role their periods of subaerial exposure may have played in the climate and ecology of the regions around them. The Kerguelen hotspot did not stay in one place as the tectonic plates moved over it. From the perspective of the hotspot, fixed in the deep mantle, the plates above it drifted past, and the hotspot left a trail of volcanic features across the ocean floor that records the movement of the plates like a pen dragged across paper. This trail is called a hotspot track, and the Kerguelen hotspot produced one of the longest and most clearly defined hotspot tracks on Earth. The track runs from the plateau itself northward along the 90 East Ridge, a remarkably straight volcanic ridge that runs almost due north through the Indian Ocean for nearly 5,000 kilometers, from the latitude of the Kerguelen Islands almost to the Bay of Bengal. The 90 East Ridge was built as the Indian Plate moved northward over the hotspot, with eruptions occurring progressively farther north along the ridge as the plate moved. The ages of volcanic rocks along the ridge decrease from south to north, from approximately 82 million years at the southern end to about 38 million years at the northern end, a perfect record of plate motion. The hotspot track extends even farther into the Indian subcontinent itself. The volcanic rocks of the Rajmahal traps in eastern India and the Salet traps in Bangladesh, dated to approximately 118 to 115 million years ago, are among the oldest features attributable to the Kerguelen hotspot, representing the very beginning of the hotspot's interaction with the Indian plate as India began moving northward. They are now thousands of kilometers from the current position of the hotspot, carried there by the movement of the Indian plate over the course of more than 100 million years. On the other side of the Indian Ocean ridge, symmetrically placed with respect to the mid-ocean ridge that separates the Indian and Antarctic plates, lies Broken Ridge, a submarine plateau that was once contiguous with the Kerguelen Plateau before the mid-ocean ridge passed between them and began separating the two pieces. The separation between Broken Ridge and the Kerguelen Plateau began approximately 95 million years ago and has continued ever since, so that the two features are now separated by hundreds of kilometers of oceanic crust that has formed between them as the plates have moved apart. The hotspot track tells the story of the Indian Ocean's opening in a way that no other evidence can, providing a continuous record of plate motion that extends from the continental rocks of India to the remote islands of the Southern Ocean. It is one of the clearest demonstrations of the plate tectonic principle that exists on Earth's surface, a line of evidence connecting the geological history of an entire ocean basin to a single persistent source of heat deep in the mantle. Understanding the full hotspot track is also essential for reconstructing the complete tectonic history of the region. The connections between the plateau, Broken Ridge, the 90 East Ridge, and the continental trap basalts of India and Bangladesh form a system of evidence that can be used to test reconstructions of past plate positions and to refine our understanding of how the Indian Ocean opened. Each new geochronological measurement, each new geochemical analysis of rocks from the ridge or the plateau, adds a constraint that either confirms or challenges existing reconstructions, and the gradual accumulation of these constraints has substantially improved our understanding of the Indian Ocean's history over the past 3 decades of intensive research. The hotspot track also contains information about how the rate of plate motion has changed over geological time, with the spacing between dated volcanic features along the 90 East Ridge reflecting the varying speeds at which the Indian plate moved northward during its long journey from the southern hemisphere toward Asia. The scientific understanding of the Kerguelen Plateau was transformed by a series of ocean drilling expeditions, culminating in Ocean Drilling Program Leg 183 in the late 1990s, which recovered some of the most scientifically significant sediment and rock cores ever brought up from the deep ocean floor. The Ocean Drilling Program, which operated the drill ship JOIDA's Resolution, was designed to recover continuous records of sediment and rock from the seafloor in order to study the Earth's geological and climate history. The Kerguelen Plateau was a target of multiple drilling expeditions because of its unusual character and the questions it raised about the nature of large igneous provinces and the history of the southern Indian Ocean. Leg 183 drilled at several sites across the plateau and recovered material that answered some of the most important outstanding questions while opening new ones. The evidence for subaerial exposure, the periods when the plateau was above sea level, was recovered at multiple sites in the form of the soils, charcoal, wood fragments, and river conglomerates described earlier. The consistency of this evidence across multiple drill sites spread across the plateau confirmed that the subaerial periods were widespread, not local anomalies. The drilling also recovered basaltic basement rocks, whose geochemistry told a complex story about the origin of the plateau. Chemical analysis of the rocks revealed that some of them had incorporated material from continental crust, a signature that is distinctive, and that confirmed what other evidence had suggested, that parts of the Kerguelen Plateau were built on or incorporate fragments of ancient continental crust derived from Gondwana, not purely volcanic rock erupted from the mantle. The Zealandia Bank, a prominent feature extending westward from the central plateau, provided particularly clear evidence for this. Samples recovered from ODP Site 1137 on the Zealandia Bank included gneissic metamorphic rocks and felsic igneous clasts, rock types that are characteristic of continental crust rather than oceanic or volcanic rock. Gneiss is a type of rock that forms deep in the crust under high temperature and pressure conditions over millions to hundreds of millions of years, and it has no business being in the middle of an oceanic plateau unless that plateau incorporates fragments of ancient continental crust. The Zealandia Bank gneisses are thought to be fragments of the Gondwana continent that were left behind as India moved northward, incorporated into the growing plateau by the same volcanic processes that built it. The drilling also revealed the detailed stratigraphy of the sediments overlying the volcanic basement, recording the transition from the subaerial and shallow marine conditions of the Cretaceous to the deep marine conditions of the present. This sedimentary record is a continuous archive of environmental change spanning tens of millions of years, capturing the cooling of the Cretaceous greenhouse, the opening of the ocean gateways that transform Southern Ocean circulation, and the progressive sinking of the plateau below the photic zone where photosynthesis occurs. The Ocean Drilling Program expeditions to the Kerguelen Plateau also served as a model for international scientific collaboration in oceanography. The JOIDA's Resolution carried scientists from dozens of countries, whose different analytical capabilities and perspectives enriched the scientific yield of each drilling cruise. The sediment cores recovered by those expeditions are stored in core repositories around the world, where they remain available for reanalysis using techniques that did not exist when the original drilling was done. New methods of geochemical analysis, new dating techniques, and new computational approaches have allowed researchers to extract more information from the existing cores than was possible at the time of recovery. And the Kerguelen Plateau Archive continues to yield new scientific results decades after the drilling was completed. The image of dense forests growing on the Kerguelen Plateau during the age of the dinosaurs is one of the more evocative facts in its geological story, and it deserves to be held in the imagination for a moment before we move on. The Cretaceous period, which lasted from approximately 145 to 66 million years ago, was the warmest sustained period in the last 200 million years of Earth history. There were no permanent polar ice caps. Sea levels were 60 to 80 meters higher than today. The average global temperature was several degrees warmer, and the distribution of climate zones across the Earth was different from anything in human experience. Forests grew at high latitudes that are today covered by tundra or ice sheets, and the southern high latitudes, where the Kerguelen microcontinent was located, had a temperate to subtropical climate rather than the sub-Antarctic climate that characterizes the region today. In this warm world, the Kerguelen microcontinent was positioned in the southern Indian Ocean at latitudes somewhat lower than its present position, because the Antarctic plate has moved southward over the tens of millions of years since. The climate was warm enough for conifers to thrive, and the Araucarian pines and cypresses whose fossil wood has been recovered from the drill cores were well adapted to the conditions of the Cretaceous southern forests. Araucarian conifers are an ancient lineage, already well established during the Jurassic period, and they were a dominant component of the southern forests throughout the Cretaceous. Living Araucarians include the distinctive monkey puzzle tree of South America, the Norfolk Island pine, and the bunya pine of Australia, trees that retain their ancient southern distribution as a relic of the once continuous Gondwana flora. The fossil record shows that Araucarians were present across all the southern landmasses during the Cretaceous, from what is now Antarctica to New Zealand to South America to Africa, in a distribution that reflected the connected geography of Lake Gondwana. The Kerguelen microcontinent, in its forested period, was part of this world. Its forests may have been seeded by spores and seeds carried by wind or water from the nearby continental landmasses, or they may represent a colonization by plants that were already present on the fragments of Gondwana crust incorporated into the plateau. The wildfires evidenced by the charcoal in the drill cores suggest that the plateau was dry enough in some seasons for fires to ignite, whether from lightning or from the heat of nearby volcanic activity, and the forest was substantial enough that fires left a detectable record in the sediments. What animals inhabited these forests is unknown, because the fossil record from the Kerguelen Plateau does not include any animal remains. The remoteness of the microcontinent from the major continental landmasses, and the uncertainties about whether it was ever connected to any of them by land bridges, make it unclear what the fauna might have been. But the flora was rich enough to leave a record that has survived 100 million years of burial under the ocean, and the existence of that record is itself a reminder of how much of Earth's biological history we have not yet found. What we can say about the forests of the Kerguelen microcontinent is that they were not isolated curiosities, but part of a broader pattern of Cretaceous southern hemisphere vegetation that extended across all the Gondwana-derived landmasses. Antarctica itself, in the Cretaceous, was not the frozen continent it is today, but a forested landmass at high southern latitudes, supporting conifer forests and other vegetation in the continuous daylight of polar summer. The connection between the Kerguelen flora and the Antarctic flora, implied by the shared Araucarian and Cypress lineages in the fossil record, is consistent with the botanical evidence for a broadly connected southern flora that persisted through much of the Mesozoic and into the early Cenozoic. The sinking of the Kerguelen microcontinent was one chapter in the fragmentation of that connected world, as the opening of ocean gateways isolated the southern landmasses from each other and from the floating islands that had once been part of the same continuous forest. The three periods of subaerial existence represent three separate chapters in the story of the Kerguelen microcontinent, each with its own geography, its own climate, and its own ecological character. The earliest period, around 100 million years ago, occurred in the warmest part of the Cretaceous, when the microcontinent's position was somewhat farther north than it is today, and the climate was subtropical rather than subantarctic. The later periods occurred in a cooling world, as the global Cretaceous warmth gave way to the progressive cooling of the Cenozoic, and the microcontinent had drifted to higher latitudes on the moving Antarctic plate. Each period of emergence would have had a different character, and the fossil record preserves evidence of different environments at different drill sites, reflecting this temporal and geographical diversity. The physical evidence for subaerial existence is also evidence for a particular kind of geological process, the ability of large igneous provinces to maintain significant portions of their area above sea level for extended periods despite the general tendency of oceanic crust to subside as it cools. The Kerguelen Plateau managed this through the combination of its extraordinary thickness, in places more than 30 kilometers compared to typical oceanic crust of 5 to 8 kilometers, the buoyancy provided by the partly continental material in its foundation, and the periodic renewal of volcanic activity that added new material and raised the plateau back above the waterline. Understanding how these factors interacted, and what proportion of each was responsible for maintaining the plateau at or above sea level during each of its subaerial periods, is one of the scientific questions that continues to be investigated using the drill core archive. The submergence of the Kerguelen microcontinent was not a sudden event. It was a slow, geological timescale process driven by the same physics that governs the behavior of all oceanic crust, and understanding why it sank requires understanding something fundamental about the difference between oceanic and continental crust and how they interact with the underlying mantle. Continental crust is thick, typically 30 to 40 kilometers, and it is made of relatively light rock, dominated by silica-rich minerals like granite and quartz. Because it is thick and light, continental crust floats high on the underlying mantle, in the same way that a thick piece of wood floats higher in water than a thin piece. This is why continents stand above the ocean floor, and why the continents have remained above sea level for billions of years, despite the constant erosion that wears them down. Oceanic crust is different in almost every way. It is thin, typically 5 to 10 kilometers, and it is made of denser rock, dominated by basalt and gabbro. And crucially, it cools and contracts as it moves away from the mid-ocean ridges where it is created, becoming progressively denser and thinner over time. Young oceanic crust, near the ridge, stands relatively high. Old oceanic crust, far from the ridge, has subsided to the depths of the abyssal ocean floor. This process of thermal subsidence is one of the fundamental dynamics of ocean basin evolution. The Kerguelen Plateau, despite its partly continental origin, is also subject to this subsidence process. The volcanic rock that makes up most of its volume is of oceanic composition, and it cools and subsidences over time. The buoyancy that kept the plateau above sea level in the Cretaceous was provided partly by the heat of the active hotspot beneath it, which inflated the lithosphere and kept it elevated, and partly by the sheer thickness of the volcanic pile that the eruptions had built up. As the hotspot activity declined over time and the plateau moved away from the hotspot and cooled, both sources of buoyancy decreased. The first submergence, around 100 million years ago, was followed by a renewed period of volcanism that raised the plateau back above sea level, and this cycle repeated at least twice more before the final submergence approximately 20 million years ago. The final sinking coincided with a period of greatly reduced volcanic activity at the hot spot, when the thermal support that had previously kept the plateau elevated was no longer sufficient to counteract the long-term cooling and subsidence of the oceanic crust. The sinking was not dramatic in any human sense. It happened over millions of years, too slowly for any observer to perceive. But the result was the disappearance of a landmass larger than Spain beneath 1 to 2 kilometers of water, a submergence that was in some sense the reverse of the tectonic uplift that has produced mountain ranges across the world, the ocean reclaiming territory that the Earth's internal heat had temporarily elevated above its surface. The pattern of emergence and resubmergence that characterized the Kerguelen microcontinent before its final sinking is also recorded in the biology of the sediments, which show transitions between shallow water marine fossils, indicating near-surface conditions, and terrestrial indicators, and then back to deeper water marine fossils as the plateau cycled above and below the waves. Each transition records the response of the local ecosystem to the changing conditions, with shallow marine communities colonizing the submerging platform during the descent and terrestrial vegetation returning during the re-emergence. This cyclical record is one of the more complete natural experiments in the geological history of island biogeography, a record of how ecosystems respond to repeated cycles of island formation and destruction on geological timescales. The comparison between the Kerguelen Plateau and the myth of Atlantis is one that scientists have made, carefully, and with appropriate caveats, because the parallel is genuinely striking, even though the specifics are entirely different. Plato's account of Atlantis, written in the 4th century before the Common Era, describes a powerful civilization on a large island in the Atlantic Ocean that was submerged beneath the sea in a single day and night, as divine punishment for its people's moral failings. The myth has been endlessly reinterpreted, and the search for a real geographical basis for it has produced an enormous literature, mostly unpersuasive, linking Atlantis to everything from the island of Thera in the Aegean to the Caribbean to Antarctica. The Kerguelen Plateau is not Atlantis in the mythological sense. It was not the home of a civilization. It was not submerged in a catastrophic event. It did not sink in a day or a night, but over millions of years. And it lies in the Indian Ocean, not the Atlantic. But in a geological sense, the Kerguelen Plateau is more literally an Atlantis than anything else on Earth. It was a real continent, large enough to deserve that name, that genuinely existed above the sea surface, that genuinely sank beneath the waves, and that is now genuinely hidden under the ocean, leaving only a scattering of small islands as testimony to what was once a substantial landmass. The evidence of its existence above the sea is preserved in the drill cores, in the charcoal and the wood and the river stones, just as one might imagine the evidence of a lost civilization being preserved in some physical record. The analogy is useful not because it suggests any mystical connection, but because it illustrates something that geology teaches repeatedly. The Earth's surface is not permanent. What is land today was ocean yesterday, in geological terms, and what is ocean today was once land. The Kerguelen microcontinent sank 20 million years ago, which is a long time in human terms, but a recent event in the 4.5 billion year history of the planet. Before it sank, it was as real and as above water as any continent that exists today. The scientific community that studies large igneous provinces and oceanic plateaus has embraced the real Atlantis framing as a way of communicating the genuinely remarkable nature of the Kerguelen story to a broader audience, while being careful to distinguish between the geological reality and the mythological narrative. The geological reality is strange enough to require no embellishment. A forested continent, larger than several European nations combined, grew from volcanic eruptions in the middle of an ocean, stood above the waves for 80 million years through multiple cycles of submergence and re-emergence, and then finally sank for the last time, leaving behind a handful of remote islands as the only visible evidence of what had been there. The Kerguelen story also highlights something that the Atlantis myth, despite its fictional character, captures correctly: that lost places leave evidence, and that evidence can be found if you look in the right places with the right methods. The mythological Atlantis, if it had been real, would have left physical traces in the sediment and rock of whatever ocean basin it lay in, just as the real Kerguelen microcontinent has left its traces in the drill cores recovered by oceanographic expeditions. Science is, among other things, the systematic search for the evidence of things that cannot be directly observed, and the Kerguelen Plateau is one of its most rewarding subjects. The islands that today mark the summit of the sunken plateau are among the most remote permanently inhabited places on Earth, and they have a character that reflects their extraordinary geographical isolation. The Kerguelen Islands, officially the Kerguelen Archipelago, are a French overseas territory located at approximately 49 degrees south latitude and 69 degrees east longitude in the southern Indian Ocean, roughly equidistant between the southern tips of Africa, Madagascar, and Australia. The nearest continent is Antarctica, approximately 2,000 kilometers to the south. The nearest inhabited settlement before the French research station established there is thousands of kilometers away. The main island, Grande Terre, is the largest, covering about 6,700 square kilometers, roughly the size of Delaware, and it is dominated by a mountainous interior that includes the Cook Glacier, one of the largest glaciers in the sub-Antarctic region, and Mount Ross, the highest point, which reaches nearly 2,000 meters above sea level. The coastline is extraordinarily indented, with hundreds of fjords and peninsulas created by glacial erosion during the Pleistocene ice ages. The climate is harsh by any standard. The islands lie within the roaring 40s and the furious 50s, the latitude bands of the Southern Ocean, where westerly winds blow almost continuously and are interrupted only by storms. Average wind speeds at the archipelago are among the highest measured anywhere in the world, and the weather is persistently overcast, wet, and cold, though the sub-Antarctic location prevents the most extreme polar conditions. Snow can fall in any month. Sunlight is scarce and often obscured by low cloud. Despite this, the islands are extraordinarily rich in wildlife. Millions of seabirds, including albatrosses, petrels, and penguins, nest here, taking advantage of the productive waters of the Southern Ocean that surround the plateau. Elephant seals and fur seals haul out on the beaches. The waters around the plateau are some of the most biologically productive in the Southern Ocean, a consequence of the way the plateau deflects the Antarctic circumpolar current and creates conditions favorable for the upwelling of nutrient-rich deep water. The French have maintained a permanent research presence at Port-au-Français, a base on the main island, since the 1950s, and the station currently supports a small community of researchers and support staff who study the biology, oceanography, geology, and atmospheric science of this remote region. The Kerguelen Islands were designated a UNESCO World Heritage Site, a recognition of both their exceptional natural values and the scientific importance of the broader plateau that lies beneath the surrounding ocean. The designation reflects a growing international recognition that the Kerguelen region, precisely because of its remoteness and its relative freedom from direct human impact, constitutes one of the most important natural laboratories in the Southern Ocean for understanding the baseline state of subantarctic ecosystems and the geological processes that sustain them. The history of human encounter with the Kerguelen Islands is brief by the standards of most inhabited places on Earth, and it has a character shaped entirely by the extraordinary remoteness of the archipelago. French explorer Yves-Joseph de Kerguelen discovered the islands in 1772 and initially reported them as a large southern continent. The legendary Terra Australis that European navigators had been seeking for centuries. He was wrong, and subsequent expeditions established that the islands were merely an archipelago, but the name stuck. James Cook visited in 1776 and was characteristically unimpressed, describing the islands as desolate and naming them the Island of Desolation, a name that did not persist. The islands were used by sealers and whalers throughout the 19th century, who hunted the seal and whale populations to near extinction before the populations recovered under modern protection. Rabbit populations introduced by 19th century mariners have had a significant impact on the native vegetation and continue to be managed by conservation programs today. The Kerguelen Plateau, despite being submerged under 1 to 2 kilometers of water, is far from biologically inert. The submarine plateau and the waters above it support an ecosystem of remarkable richness and diversity, and the geological structure of the plateau plays a direct role in creating the conditions that make this richness possible. The key is the interaction between the plateau and the Antarctic circumpolar current, the massive eastward-flowing current that circles Antarctica and is the dominant feature of Southern Ocean circulation. The circumpolar current carries an enormous volume of cold, dense, nutrient-rich water eastward, but when it encounters the Kerguelen Plateau, which rises 2,000 meters above the surrounding ocean floor, it is deflected northward and southward around the plateau. This deflection creates complex patterns of upwelling and mixing that bring nutrient-rich deep water to the surface, creating conditions that support dense phytoplankton blooms and the entire food chain that depends on them. The result is a zone of high biological productivity that stands out even in satellite images of ocean color, the Kerguelen region appearing in the deep blue of the Southern Ocean as a patch of green-tinged water indicating the presence of phytoplankton. This bloom supports massive populations of zooplankton, particularly Antarctic krill, which in turn supports the whales, penguins, seabirds, and fish that make the Kerguelen region one of the richest marine environments in the southern hemisphere. Sperm whales, minke whales, and humpback whales visit the southern end of the plateau during the austral summer to feed on the abundant krill and squid that concentrate in the productive waters. King penguins from the Kerguelen Islands make long foraging trips out over the plateau, diving hundreds of meters to catch fish and squid in the cold water column. Patagonian toothfish, a large and slow-growing fish of commercial importance, live on and near the sea floor of the plateau, and the management of this fishery has been one of the central conservation challenges in the Kerguelen region. The deep sea floor of the plateau itself supports benthic communities of sponges, corals, sea urchins, and other invertebrates adapted to the cold, dark, and high-pressure conditions of the deep sea. These communities have been surveyed by research vessels and remotely operated vehicles, revealing a complex and diverse fauna whose distribution is shaped by the geological structure of the plateau, with different communities in the sediment-covered basins and on the exposed rocky slopes and ridges. The Kerguelen Plateau is thus not simply a geological curiosity, but a living ecosystem, sustained in its biological richness by the very geological structure that makes it scientifically interesting. The same features that create the unusual oceanographic conditions, the shoaling of the seafloor by the volcanic plateau, the deflection of the circumpolar current, the creation of upwelling zones, are directly traceable to the geological history we have been tracing. The eruption of the hotspot, the building of the plateau, the slow subsidence of the continent beneath the waves. There is a beautiful continuity in this. The same geological event that built a forested continent 100 million years ago is responsible, through its sunken remnant, for some of the most productive marine ecosystems in the Southern Ocean today. The plateau that supported conifer forests in the age of the dinosaurs now supports whale populations and penguin colonies and fish communities in the cold waters that cover it. The ecological richness has shifted from terrestrial to marine, from forests to phytoplankton blooms, but the geological foundation that makes it possible has remained the same. The ancient volcanic plateau built by a hotspot that is still active, still erupting at Heard and McDonald Islands, still contributing to the biological productivity of one of the most remote and most important ocean regions on Earth. Not everyone in the geological community agrees about the extent of continental crust beneath the Kerguelen Plateau, and the debate, which has been ongoing for decades, reflects genuine scientific uncertainty about a feature that is difficult to study precisely because it lies under kilometers of water and overlying volcanic rock. The evidence for continental crust beneath parts of the plateau is strong but not complete. The gneissic rocks recovered from the Eland Bank are the clearest direct evidence, because metamorphic rocks of this type can only form within continental crust under specific conditions of heat and pressure that do not occur in oceanic settings. The geochemical signatures of continental material in many of the basaltic rocks from the plateau indicate that the magmas that formed those rocks incorporated material from pre-existing continental crust as they passed through it, and the seismic structure of parts of the plateau, specifically the thickness and velocity structure of the crust, is more consistent with continental crust than with the thin oceanic crust that underlies most large igneous provinces. But a study published in 2025 using new deep seismic reflection and refraction data across the southernmost portion of the Kerguelen Plateau found that the seismic velocity structure of the southern plateau is more consistent with oceanic igneous crust than with continental crust, suggesting that the continental material, if present, is concentrated in specific regions rather than underlying the plateau as a whole. This result adds nuance to the picture without resolving it, because it applies to only one portion of a feature that extends over more than 1 million square kilometers. The scientific consensus that has emerged from decades of research is that the Kerguelen Plateau is a composite structure, with its origin involving a combination of processes. The core of the plateau, particularly the central and southern portions, is thought to incorporate fragments of continental crust from Gondwana that were stranded in the developing Indian Ocean as the breakup proceeded, surrounded and partly covered by the enormous volumes of volcanic rock generated by the hotspot. Other portions, particularly the northern plateau, appear to be more purely volcanic in origin, built entirely from mantle-derived magma without a significant continental component. This composite origin is what makes the Kerguelen Plateau scientifically unique among large igneous provinces, and it is what justifies describing parts of it as a microcontinent rather than simply a volcanic plateau. The distinction matters not just for classification, but because it has implications for our understanding of how Gondwana broke apart, which fragments of continental crust ended up where, and how the tectonic and volcanic processes that shaped the southern Indian Ocean interacted with each other over the 130 million years of the plateau's geological history. The ongoing debate about the extent of continental crust beneath the Kerguelen Plateau also illustrates the difficulty of studying geological features that are buried under water and overlying sediment. The best available tools for investigating the crustal structure of the deep ocean floor, seismic surveys and deep drilling, provide information that is inevitably incomplete and that requires interpretation under assumptions that may themselves be uncertain. Different research groups using different datasets and different analytical approaches have reached somewhat different conclusions. Not because any of them is doing poor science, but because the feature is genuinely complex and the data genuinely ambiguous in ways that make confident conclusions difficult. This ambiguity is itself informative, reflecting the unusual character of the Kerguelen Plateau as a feature that combines volcanic and continental elements in proportions and configurations that have no good modern analog. The 90 East Ridge is one of the most geometrically perfect features in all of the world's oceans, and it tells a story that connects the Kerguelen Plateau to the geological history of the Indian subcontinent in a way that no other evidence can. The ridge runs almost exactly due north from approximately 30 degrees south latitude to the Bay of Bengal, a distance of nearly 5,000 kilometers, following the 80th meridian of east longitude with remarkable fidelity. It is a submarine ridge, mostly beneath the ocean, but rising to within a few hundred meters of the surface in places and breaking the surface in the Cocos Islands and Christmas Island at its northern end. The ridge was built as the Indian plate moved northward over the Kerguelen hotspot, with the hotspot continuously erupting and building new volcanic material onto the trailing edge of the moving plate. The age of the volcanic rocks increases from north to south along the ridge, from approximately 40 million years at the northern end to 82 million years at the southern end, a perfect record of the Indian plate's northward movement. The rate of movement implied by these ages, calculated by dividing the distance between points of known age by the time difference between them, is consistent with the rates derived from the magnetic anomaly patterns in the ocean floor, the stripes of alternating magnetic polarity that record the history of seafloor spreading, and from which the movements of tectonic plates are reconstructed. The 90 East Ridge essentially serves as an odometer for the Indian plate, recording its journey from near the Kerguelen hotspot in the Cretaceous to its current position on the far side of the Indian Ocean. The northern end of the 90 East Ridge disappears beneath the sediment of the Bengal Fan, the massive accumulation of sediment deposited at the mouth of the Ganges and Brahmaputra rivers, which has buried the older portions of the ridge under kilometers of river-derived mud. But the connection between the ridge and the Indian subcontinent is documented by the Raj Mahal and Sulhet trap basalts in eastern India and Bangladesh, continental flood basalts that represent the very beginning of the Indian plate's transit over the Kerguelen hotspot, before the plate had moved far enough for the volcanism to be entirely oceanic. The 90 East Ridge is, in this sense, a thread connecting two very different geological environments. The remote subantarctic plateau, that is our main subject tonight, and the densely populated river plains of eastern India and Bangladesh, where the oldest rocks associated with the Kerguelen hotspot are now buried under the Himalayan erosion products that have filled the Bengal Basin. The same mantle plume that built the forests of the Kerguelen microcontinent also produced the basalt flows that underlie the rice fields of Bengal, and the connection is written in the ages of the rocks along a straight line across the Indian Ocean. The hotspot track also contains information about how the rate of plate motion has changed over geological time. The spacing between dated volcanic features along the 90 East Ridge is not perfectly uniform, reflecting variations in the speed at which the Indian plate moved northward during its long journey from the southern hemisphere toward Asia. The Indian plate is known to have had one of the fastest rates of motion of any tectonic plate in geological history, moving northward at times at rates of up to 20 centimeters per year, roughly twice the typical rate of modern plate motion. That extraordinary speed is recorded in the geometry of the hotspot track, in the widely spaced volcanic features that mark the rapid phases of movement and the more closely spaced features that record the slower periods. The connection between the 90 East Ridge and the subcontinent is part of a broader pattern of geological connections across the Indian Ocean that have been assembled, piece by piece, over the past several decades of oceanographic and geophysical research. The Indian Ocean is in some ways the least understood of the major ocean basins because its complex tectonic history, involving multiple phases of rifting and spreading, and the extraordinarily rapid northward movement of the Indian plate, has produced a seafloor that is unusually heterogeneous and difficult to interpret from the standard tools of plate tectonic analysis. The Kerguelen hotspot track, with its clear age progression and its connections to both continental and oceanic geological features, is one of the clearest threads through this complexity, a reference frame against which other features of the Indian Ocean's evolution can be understood. Understanding the full hotspot track is also essential for reconstructing the complete tectonic history of the region. The connections between the plateau, Broken Ridge, the 90 East Ridge, and the continental trap basalts of India and Bangladesh form a system of evidence that can be used to test reconstructions of past plate positions and to refine our understanding of how the Indian Ocean opened. Each new geochronological measurement, each new geochemical analysis of rocks from the ridge or the plateau, adds a constraint that either confirms or challenges existing reconstructions, and the gradual accumulation of these constraints has substantially improved our understanding of the Indian Ocean's history over the past 3 decades of intensive research. The Kerguelen Plateau, in its submerged state, plays a role in the present-day climate system that is disproportionate to the attention it receives in popular discussions of ocean science. The Southern Ocean is the most important body of water on Earth for climate regulation, and this is not an exaggeration. It is the primary conduit through which heat is exchanged between the surface ocean and the deep ocean, through a process called deep water formation and circulation that is ultimately responsible for distributing heat across the entire planet. The Southern Ocean absorbs more heat and more carbon dioxide from the atmosphere than any other ocean basin, making it a critical buffer against the worst effects of climate change. And the dynamics of the Southern Ocean are profoundly influenced by the bathymetry, the underwater topography, of its floor. The Kerguelen Plateau is the second largest submarine plateau in the world, and its presence in the path of the Antarctic circumpolar current creates one of the most significant topographic obstacles in the entire Southern Ocean. The current cannot simply flow over the plateau unimpeded, because the plateau rises 2,000 meters above the surrounding floor, and at its shallowest points the water above it is only about 1,000 meters deep, much shallower than the depths to which the deep water masses of the circumpolar current extend. The deflection of the current around and over the plateau creates persistent patterns of upwelling, where deep water from below the thermocline is brought to the surface by the complex flow patterns around the topographic obstacle. This upwelling brings not only nutrients but also carbon dioxide to the surface, and the exchange of carbon dioxide between the ocean surface and the atmosphere in the Kerguelen region is an important component of the global carbon cycle. The biological productivity stimulated by the plateau-driven upwelling, the phytoplankton blooms that turn the surrounding waters green in satellite images, is not just ecologically important but climatically significant, because the phytoplankton absorb carbon dioxide from the atmosphere as they grow, and when they die their organic material sinks to the seafloor, sequestering carbon in the deep ocean. The Kerguelen Plateau is, in this sense, a carbon pump, a geological feature that has been mediating the exchange of carbon between the atmosphere and the deep ocean for millions of years. Understanding the contribution of the Kerguelen region to the global carbon cycle is one of the active research priorities in Southern Ocean science, because it bears directly on the question of how much carbon the ocean can absorb as atmospheric carbon dioxide continues to rise. The same geological structure that once supported forests in the age of the dinosaurs is now a key player in the regulation of Earth's present climate, a connection that spans 100 million years of geological and ecological transformation. The Southern Ocean as a whole currently absorbs approximately 40% of the carbon dioxide that human activities release into the atmosphere, making it the single most important natural carbon sink on the planet. If this absorption capacity changes as the ocean warms, or as circulation patterns shift in response to climate change, the consequences for atmospheric carbon dioxide concentrations and the rate of global warming would be significant. The Kerguelen Plateau, as one of the major topographic features shaping Southern Ocean circulation and biological productivity, is therefore not just a geological curiosity or a historical archive, but a living component of the Earth system whose behavior in a changing climate matters. Research programs focused on the Kerguelen region are as much about the future as they are about the past, seeking to understand a system that will play a critical role in determining how rapidly the climate changes in the coming centuries. The Kerguelen Plateau is, above all else, a demonstration of the timescales on which the Earth operates and the humility those timescales should inspire. 130 million years ago, where the southern Indian Ocean now lies, there was land being torn apart by tectonic forces, flooded by eruptions from a hotspot in the deep mantle, and assembled into a new landmass that would spend the next 80 million years intermittently above the waves. Forests grew, rivers flowed, fires burned and left their ash in the sediment. The plateau was, for long periods, as real and as present as any continent that exists today, a place where the processes of life and geology interacted in the ways they always have when land and sea and atmosphere come together. And then, 20 million years ago, it sank. Not catastrophically but inevitably, as the thermal support provided by the hotspot beneath it waned and the cooling oceanic crust resumed its long subsidence toward the abyssal depths. The forests were replaced by cold ocean water. The rivers became submarine canyons. The mountain peaks became seamounts, and eventually most of them sank below the photic zone, where sunlight no longer reaches and the elaborate ecosystems that light supports cannot survive. What the Kerguelen Plateau tells us about the Earth is that the boundary between land and ocean is not a permanent feature of the planet's geography, but a temporary equilibrium between competing forces, maintained only as long as the internal heat and tectonic dynamics that support it remain in the right balance. Every continent that exists today will eventually be worn down or subducted or fragmented by the geological processes that are always operating, and every ocean basin that exists today was once dry land or will eventually be again, on the timescales of hundreds of millions of years on which plate tectonics operates. The Kerguelen story is also a story about the connections between geological and biological history, about how the physical evolution of the Earth creates and destroys the habitats that life requires. The forests of the Kerguelen microcontinent were not separate from the geology that produced them, but were a direct consequence of it, possible only because the hotspot had built a landmass large enough and stable enough for forests to establish themselves in a warm Cretaceous climate. When the geology changed and the land sank, the forests went with it, their legacy preserved only in the fossil record recovered by drill ships 100 million years later. Every geological feature on Earth has a story of this kind, a history of creation and transformation that connects the deep time of the planet's interior to the surface where life exists. Most of those stories are incomplete, obscured by erosion and burial and the overwriting of geological records by later events. The Kerguelen Plateau is unusual in the completeness of its story, made possible by the preservation of sedimentary records in the drill cores, and that completeness makes it one of the most instructive examples we have of how the Earth works on the timescales that matter most. The timescales of the Kerguelen story are worth sitting with, because they are among the features of geology that most consistently produce a kind of vertigo in anyone who spends time thinking about them. 130 million years ago, a number that contains within it the entire history of the mammals as a group, the entire history of the flowering plants that cover most of the land surface of the Earth today, the entire history of the Antarctic ice sheet that shapes global climate, and the entire history of human beings and their ancestors from the earliest primates to the present. The Kerguelen hotspot was already old by the time the first primates evolved. The microcontinent had already risen and sunk and risen again by the time the first grasses appeared. And 20 million years ago, when the plateau made its final descent beneath the waves, the ancestors of the great apes were just beginning the lineage that would eventually produce a species capable of drilling holes in the seafloor to recover charcoal from fires that burned before their own phylum had diversified into anything recognizable. As you lie in the dark tonight, the Kerguelen Plateau lies under more than a kilometer of cold water, 2,000 kilometers from the nearest inhabited continent, in one of the most remote and least visited parts of the world ocean. The light does not reach it. The temperature is close to freezing. The pressure at the seafloor is 100 or more times the pressure at the surface. And beneath the sediment that has slowly accumulated over the 20 million years since the plateau finally submerged, beneath the layers of diatom ooze and clay and volcanic ash, the charcoal of ancient fires is still there. The wood fragments of trees that grew in a warm Cretaceous climate are still there. The rounded river stones that were carried by rivers that flowed on land that no longer exists above the sea are still there. These are the physical memories of a world that ended before any mammal larger than a cat had evolved, before the first grasses appeared, before the asteroid impact that ended the age of the dinosaurs, in a time so remote that our entire evolutionary lineage from ape to human fits into less than 1% of the interval since those fires burned. And yet the evidence is there, preserved in the rock and sediment with a fidelity that allows scientists today to reconstruct the forests, the climate, the geological events of a microcontinent that no human has ever seen above water and never will. This is what geology does at its best. It reads the past in the physical record that the past has left behind, translating the language of rock and sediment into the history of a world that is gone. The Kerguelen Plateau will not rise again. The conditions that produced it, the combination of Gondwana breakup, hotspot activity, and Cretaceous warmth that briefly assembled a continent in the southern Indian Ocean, do not exist anymore. And the geological conditions that would be required to raise it above the waves again are not developing. It will continue to subside slowly as the oceanic crust beneath it continues to cool and contract, moving gradually toward the depths. The Kerguelen Plateau will not rise again. The conditions that produced it, The combination of Gondwana breakup, hotspot activity, and Cretaceous warmth that briefly assembled a continent in the southern Indian Ocean do not exist anymore, and the geological conditions that would be required to raise it above the waves again are not developing. It will continue to subside slowly, as the oceanic crust beneath it continues to cool and contract, moving gradually toward the depths. But the record it left in the rock and in the drill cores that scientists have brought up from those depths is permanent in its own way. A library of geological time that tells the story of a continent that grew and flourished and sank, and that now exists only in the data and the memories that human science has assembled from the silence of the deep. That library is still being read. New analytical techniques allow researchers to extract more information from existing core samples than was possible when the drilling was done. New deep seismic surveys continue to refine our understanding of the crustal structure beneath the plateau. New biological surveys of the seafloor and water column are building a more complete picture of the ecosystem that the sunken continent now supports. The Kerguelen Plateau is not a closed chapter, but an ongoing investigation, a place where each new study adds a detail to a picture that is still being assembled. The story of the Kerguelen Plateau is also, in the end, a story about patience, about the kind of time that geology requires, and the kind of attention that science can pay to places that most people will never visit, about phenomena that are invisible to ordinary experience, but that are as real as anything that exists. The forested continent that once stood here was as real as any forest you have ever walked in. The river stones in the drill core were carried by a real river, in a real landscape, under a real sky. They are just very old and very far away, and buried under a kilometer of cold water at the bottom of the world. Sleep well. The lost continent lies in its deep silence, and somewhere in a laboratory, a scientist is looking at a slice of rock from its ancient forests and learning something new about a world that ended before our story had even begun.